All right. Welcome back, Time Bandits. Okay. Hopefully, everybody in Florida is safe and well. And if you're watching this from Florida, welcome to class, and I'm glad that you're still with us. That was a nasty, nasty hurricane. I distinctly remember when I was very young being in a hurricane. It was nowhere near a stage 5. But I remember the eye passed over because I remember, and I love storms. So I never felt like I was in danger. Maybe I was too young to know what was really happening. But I remember that eye, and it was beautiful inside the eye. There were clouds, there's blue sky, no wind, no rain. It was just gorgeous. And of course, it didn't last very long. So you have this enormous storm, and then all of a sudden, just this beautiful moment of weather, 10, 15 minutes, I guess. And then, of course, the storm started right back up again. Fascinating phenomenon. Maybe I should blog about that. I think I just found a topic. Anyway, today we are talking about molecular shapes. Last time we talked about Lewis dot structures and how to put things together and all that fun stuff. And aside from the bonding information, I've told you this. I told you this. Lewis dot structures are nothing but cartoons. The real problem with Lewis dot structures is that we are restricted to a two-dimensional sheet of paper, or in this case, sheet of electrons. The world is not two-dimensional. My ex-wife was, but for the most part, the world we live in is three-dimensional. Very hard to get shapes onto 3 dimensions. It's technically called a projection. We are projecting the 3-dimensional reality onto a 2-dimensional surface. And today we're going to talk about what that actual shape is. Now, the first thing we need to understand is that molecules can be very, very long, very large. You have inside your body right now, as we speak, a protein. It's called the Titan protein. It is over 100,000 amino acids long. An amino acid chain has 3 on the backbone of the amino acid chain. It has all these little things dangling off of it, but it's almost like a necklace because the proteins are just linkages of amino acid to amino acid to amino acid to amino acid. It's just a long amino acid chain. One chain, a single chain. Now it's coiled up and has all kinds of weird shapes that we're not going to get into unless we continue on into biochemistry, the biochemistry section, which currently we don't have plans to do. We can talk about it if you would like to continue after this course. We can go on and do the organic and biochemistry sections, but we don't plan on it at the moment. So when we're talking about what we're talking about today, you always have to pick a single atom out of the entire molecule. We're talking about the shape around just one element, not a single molecule, a single atom. You have to pick a single atom. We're talking about the shape around just that one atom. If you choose more than that, it gets very complicated very quickly, and it's beyond the scope of this course. So, with that in mind, let's go ahead and get started. I'm going to share the screen if I can remember how to do this. What we're talking about is pronounced VSEPR. It's spelled FSEPR. I'm going to tell you what that means in a moment, but we call it VSEPR because you cannot say VSEPR without spitting. Wipe that off there. VSEPR stands for, not that you need to know this, valence shell electron pair repulsion theory. The valence shell electron pair repulsion theory, which sounds all fancy pants and everything. Let's break it down. Molecular shape is only influenced by the valence shell electrons. As you recall, we have inner shell electrons, and the outermost electrons are called valence shell. It's only influenced by the valence shell because those are the outermost electrons. They are the outermost electrons. Excuse me. We don't have to worry about inner shell electrons. They're doing nothing. They're hiding together. They're just huddled together in the inside interior of the atom, and they don't want to participate. They just want to keep to themselves. So we only worry about the valence shell electrons. And remember, electrons live in orbitals. Orbitals are, as you recall, just little regions of space around the nucleus where you're most likely to find the electron. And those orbitals always hold two or up to two electrons. In a proper Lewis dot structure, they're all paired. So we don't have to worry about each individual atom. We only worry about pairs of atoms in their orbitals. I lost my glasses. Now, it's no big deal. They're just reader glasses. They cost like $5. I get the really expensive ones. They cost me as much as $12. But still, they're readers, and I can't really see what I'm writing, so my handwriting may not be as good as it usually is. So really, we're talking about electron pairs in orbitals in the valence shell. Repulsion is the way most women feel towards me. And since they're repulsed by me, that means they want to keep as far away from me as possible. That's what the valence shell electron pair repulsion theory says. Remember, even in orbitals, electrons are negatively charged, and like charges repel. So what we're really talking about, and this is the crux of the entire theory, the valence shell electron pairs are trying to get away from each other as far as possible. That's all there is to it. They're just repelled, so they're trying to get away from each other. Now, the theory is very simple. To work it out becomes a little more complex because remember, atoms live in 3 dimensions and we're writing in 2. But fortunately for us, it's already been done. It's all been worked out. I'm going to talk about a couple of things, and I'm going to put together a table here in a moment. Do you have to memorize this table? Of course not. We're not taking a quiz. But when I first learned this, I still remember when I first learned this, which is strange because back then we had just killed a mastodon. And it just somehow clicked in my head. It just made sense. So I remembered it very quickly. just because it was easy for me. It just came naturally to me. It may or may not come naturally to you. So if it doesn't click quite the way it did for me, doesn't mean anything. Don't worry about it. Now, my terminology, I am actually not even looking at my book today. The book probably uses different terminology than I do, but the concept is going to be exactly the same. So let's go through the terminology that I'm going to use. What do you need to use? Whatever makes sense to you. I'm going to talk about set numbers. I've seen this called all kinds of fancy pants names that sound far more professional, far more technical than set number. I don't go for that kind of jazz. I'm going to call it set number. The set number is simply the number of things arranging themselves around the central element. Okay, the number of things arranging themselves around the central element. It includes the number of atoms bonded directly to the element, and we're only talking about directly to that one specific element. I'll give you examples here soon. It's the number of atoms bonded to it plus the number of lone pairs assigned to that central element. Not the total number of lone pairs in the molecule, the number of lone pairs on that central element. Notice I'm not talking about bond order. Bond order means is it a single, double, or triple bond? Doesn't matter if it's doesn't matter what the bond order is, because even if it's a triple bond, which involves 3 bonds, remember each bond has 2 electrons, no more, no less. So for a triple bond, we're talking about 6 electrons total, 1 for each of the 3 bonds. But even then, all of those bonds are focused in the same direction. They're between the central element and the element that they're bonded to. So we're not going to worry about bond order. If we're bonded to another element, all those electrons are going in the same direction. They count as a single thing, a single item. When we talk about lone pairs, we're talking about lone pairs on the central element. Okay, we're talking about lone pairs assigned specifically to that one element. We're going to talk about parent shape. Again, your book probably has a different name for this. I've seen a myriad of names for these things. The parent shape is the way that set number is going to arrange itself. Okay, so if we have 2 lone pairs and 2 atoms bonded to a central element, that's 4 things. It's set number 4. If you try and put 4 things around a central element, they're all going to have the same parent shape. Doesn't matter if they're lone pairs, doesn't matter if they're atoms. It's always going to have the same parent shape. That's the main shape for that set number. Okay? And finally, we're going to talk about the molecular shape. Remember, lone pair electrons are sometimes called non-bonding electrons. They don't really participate in the chemistry. So when we talk about molecular shape, we don't care where the lone pair electrons are. Okay? So we're going to start with the parent shape, and then we're going to ignore the lone pair electrons. The lone pair electrons are still there. They still influence the shape, but we're only interested in the way that atoms arrange themselves around the central element. In water, we only care where the hydrogens arrange themselves relative to the oxygen. Where they arrange themselves is influenced by the lone pair electrons. But ultimately, when we talk about molecular shape, we're going to ignore the lone pair electron because we just want to know where the hydrogens lie. Okay, hopefully, if you have any quick questions, we can go through those real quick. But now that you have a general idea, we're going to put together that table. Do you have any specific questions about any of these terms so far?
Nope.
Perfect. So I'm going to make a little table here. On a big whiteboard, this is so much easier. We have more space. So we're going to look at the set number, which will give us the parent shape. Let me see if I can shrink this up a little bit. We're going to look at the set number, which will give us the parent shape. The number of lone pair to give us the molecular shape. And for each of these, we're going to do an example. I don't think I shrunk that up at all. So let's start with what we started with on Lewis dot structures. Let's start with something really simple. And I'm not going to go through the process. Hopefully now you know how to figure out the Lewis dot structures. If you have a question about any of these Lewis dot structures, I do hope that you will ask. But let's start with hydrogen. H2, the absolute simplest thing that we can start with. Okay? Now, to do this, we have to choose the central element. Doesn't matter which one we choose, the one on the left or the one on the right. I'm going to choose the one on the left because why the heck not? So how many things are around that central hydrogen? Well, obviously just one thing, another hydrogen. There are no lone pairs. There's only one element bonded to it. This is set number one. How do two things arrange themselves so that they can be as far apart as possible? Well, remember, geometrically, 2 points define a line. So the parent shape is going to be linear. Linear, 2 points define a line. So it's just straight out. That's it. That's your shape right there. We have 0 lone pairs. And here's a little hint for you. If you have 0 lone pairs, the molecular shape is identical to the parent shape. How many things are trying to arrange themselves around it? Well, they're only atoms, and therefore we don't eliminate any lone pairs, so it's linear. Linear shape. So look at nitrogen. And let's pick a central nitrogen. Again, it does not matter which one we choose. Let's choose this time the one on the right. Why not? Nitrogen is nitrogen. Oh, wait a minute. Wait a minute. I forgot something here. Let's do carbon dioxide instead. We'll do nitrogen next. Carbon dioxide. It's pretty obvious what the central element is. The central element obviously is the carbon right in the middle. We could talk about the oxygens as one of the central element. We're going to choose carbon. How many things are trying to arrange themselves around the carbon? Well, there are no lone pairs on the carbon. There's only two atoms, and those atoms are oxygens. This is set number 2. How can those two items, how can the two oxygens get as far apart from each other as possible? Well, if they're at an angle, they're close. They're closer than they need to be. To get them as far apart as possible, we want this angle right here, to be 180 degrees. Again, the parent shape is linear. There are no lone pairs on this. And when there are 0 lone pairs, the molecular shape equals the parent shape. So this is a linear molecule. This is why carbon dioxide is linear. Okay. Now let's do nitrogen. Nitrogen has a triple bond, but it doesn't matter. And I promised to use the right side nitrogen as our central element. It doesn't matter what the central element is because there's 2 nitrogens. And it doesn't matter that it's a triple bond because all those electrons are between the 2 nitrogens. They're all in the same basic region of space. Oh, yes, it's a little fluffy because you have your p orbitals above and below and front and back. And I'm sorry, pi bonds, not p orbitals, pi bonds. But they're still all oriented the same basic direction. Well, now notice we have 1 atom and 1 lone pair set of electrons. So we have this atom here, and we have this lone pair. So this is still set number 2. If the set number is the same, the parent shape is always the same. So this is linear. See, all molecules are linear. I'm kidding. Anyway, this is still set number 2, so this is still linear. But now we have 1 lone pair of electrons. So what's the molecular shape? It's linear. Now we're going to take away the lone pair of electrons. Well, guess what? We still have 2 atoms. 2 points define a line. Guess what? Nitrogen is linear. Everything's linear. God, can't we do something more interesting? Okay, should we do something more interesting?
Sure, I'm sure you will.
Okay, let's get away from linear, for crying out loud. Let's look at every embalmer's favorite compound. Formaldehyde. Obviously, we're going to use carbon as the central element. How many things are trying to arrange themselves around the carbon? Well, you should see a pattern here. We are done with set number 2. Obviously, we're on to set number what?
3.
3. How do 3 things arrange themselves around a central element so they can be as far apart as possible? Remembering that we're working in 3 dimensions. Well, as it turns out, first of all, they're not going to be linear. They're going to have to make room for each other. So all of a sudden, we have a triangle. So we're going to have some kind of a, notice I'm giving myself a little bit of space here, trigonal shape. But it's going to be flat because this angle here is, it's not 60, it must be 180 degrees. No, not 180. What's 360, 120 degrees? 120 degrees. But if it's not flat, then it's going to start, the angle this way is going to be, so the angle up and down is going to be 180. It's going to be as far apart as possible. So it's trigonal planar. They're all on a plane. They're all on the same plane. Trigonal, because it looks like a triangle. Planar. There are no lone pairs on the carbon. And what did I tell you about when there's no lone pairs on the central element? Molecular shape is the same as the parent shape. So we are still trigonal planar. And this is a good time to start talking about some of this crap. The oxygen is bigger than the hydrogen. Okay, it's going to require a little more space than the hydrogens do. So what's going to happen? I just wrote this angle as 120 degrees. But the oxygen, because it's a big, bulky oxygen, it's going to take those two hydrogens and squeeze them a little bit more closer together. But not a lot. Not a lot. Some authors are going to insist that you remember minor fluctuations in shapes. So that angle that I drew there is 120 degrees is actually a little bit less. It doesn't, does it, do you really learn anything new by memorizing that, oh, gee, it has to be a little less than 120? No, who cares? It's roughly 120 degrees. There are minor fluctuations to make space for larger elements. And while we're at it, lone pair electrons are going to need a little more space than bonds. So they're going to squeeze it a little bit more than 120 degrees. If you really want to memorize these minor fluctuations, that's fine, but you don't learn anything from it. So I wouldn't recommend that you memorize that. It's just, but always use hand waving. It's 120 degrees, give or take. And that's fine. Any questions about that?
No.
Okay. This molecule, I'm told, doesn't really exist. I'll tell you why I use it anyway. Look at NOH. NOH. We're going to use nitrogen as the central element. Nitrogen is such a weird element. Even I don't understand nitrogen. It can do things it's not supposed to be able to do. It undergoes exceptions to the octet rule all the time, but it's not supposed to be able to go through exceptions to the octet rule, because the one thing that allows exceptions to the octet rule are empty d orbitals. Nitrogen does not have empty d orbitals, and it just goes, nerds to you, I don't want to do octet, and it doesn't do it. It's just God's way of reminding us that we don't know everything. It's a model, man. There are always exceptions because we don't know everything. Everything is just a model that best fits the information available to us. Nitrogen is one of those weird elements. It says, look, you don't know. So what's the set number for this? Well, look, we have two elements. We have the oxygen, we have the hydrogen, plus we have one lone pair electron on that central element. This is set number
3.
Right, 3. And like I said, set number 3 means we're trying to put 3 things around the central element to get as far apart as possible. So the parent shape is exactly the same. But this time we have one lone pair on that nitrogen. The number of lone pairs is not 0, which means that the molecular shape will not be the same as the parent shape. So what do you have? You have basically 3 things in this lone pair. It has to take up space as well. So you have 3 things around the central element. So we start off with trigonal planar, but we only have 2 atoms attached to it. This is not 180 degrees. This is not linear. This will be closer to 120. That's basic geometry, by the way. 360 degrees divided by 3 gives you about 120 degrees. Is it going to be 120 degrees? No, because it has that lone pair electron, so it'll be squeezed a little bit, but who cares about that minor fluctuation? This molecule is bent. And that's why I use this as my example, because it reminds me of The Simpsons. Get bent, man. No. NOH. No. Such a dumb joke. So the molecular shape is actually bent. Okay? It's not flat. It just has a bend. Can't really put your hand so they're really flat anyway. So it's bent. It's just a bent molecule. This is the first time that we had a molecular shape different from a parent shape. So let's pause here and ask the basic question. Do you have any questions?
I don't think so.
Okay. Well, this pretty much wraps up. Oh, no, it doesn't. No, it doesn't. We still have one more, set number 3. Let's do oxygen. Kim, do you want to do the one on the left or the one on the right?
Oh, let's do left.
Left. Okay, oxygen. That oxygen has 2 lone pairs and 1 other atom bonded to it, so it is also set number, right, set number 3. 2 lone pairs, 1 atom, 3 things. Therefore, the parent shape is again trigonal planar. But now we have 2 lone pairs of electrons. But the shape is trivial. We only have 2 atoms here and 2 points to define a line. So of course, this is linear. It's a linear molecule. 2 points to define a line, always. A couple of ways you can remember this, if you want to remember it. If you have only 1 atom bonded to the central, it's always going to be linear because it's 2 points. 2 points to define a line. The other thing you can do is notice that 3 minus 2 only gives you 1. 1 is always going to be linear. Okay? I want to get through this table before we take our break. We are now done with set number 3. What do you suppose we're going to go to now?
4.
Excuse me. Every once in a while, people around the lake just die. And I mean entire city, entire small communities just die. It's a weird phenomenon. And when I say every once in a while, I mean once every 500 years, once every 1,000 years. We're not talking about often. But what happens is a little pocket of gas under the lake, under under the bottom, under the sediment of the lake, just goes and lets go, and it releases just enormous amounts of gas. And that gas is often methane, which is not terribly deadly, but it displaces all the oxygen. And basically what ends up happening is the entire community, they don't have any air, because for at least a moment, for long enough to actually suffocate them, it's all methane. Methane is CH4. Obviously, carbon is going to be the central element. How many things around the central element? 4. And you can clearly see, it looks like, well, there's a couple ways you can do this. Connect these things. Kind of looks like a square, doesn't it? Except what dimension are we working in?
Right.
This is not going to be a square molecule because it has 3 dimensions to work in. This parent shape is called tetrahedral. And obviously, let's just finish this line. We have 0 lone pairs, which means the molecular shape is tetrahedral. What is tetrahedral? Really hard to draw because we are trying to do this in a 3-dimensional on a 3-dimensional surface. Basically, it's going to look like almost a triangle with a 3-sided base and 1 sticking up on top. Okay. So it's almost like a triangle with 3-sided base and 1 on top. Very, very symmetrical molecule. Just hard to draw in 2 dimensions. When I was teaching, back when they used to like me, obviously they never liked me teaching, but I used to teach. I used to hand out these in my class. This is a 3-sided dice. I'm sorry, a 4-sided dice, or sometimes called a D4. This is a tetrahedral shape. Okay? And I just realized I'm on the wrong computer. I should have done this somewhere else. So if you have your book open to tetrahedral, their artist will be able to draw it a little better than I can, a lot better than I can. In fact, they use a computer to draw it. I have that program. It's just not on this computer. But it has, if you imagine the central carbon in the middle of this dice, and each point being one of the hydrogens, this is a tetrahedral shape. All right, 3 on the base in a triangular shape and 1 on top. Very, very symmetrical. Okay. If you look in the book and you find tetrahedral, let me pause here and ask, you have a question about tetrahedral before we move on?
No.
That kind of makes sense?
Mm-hmm.
So I'm continuing. Continuing the table on the next page. It's the same table. Let's look at this bad boy. Let's look at ammonia. This is ammonia. We're NH3. Again, we're still on set number 4. And if it's set number 4, the parent shape never changes. So it's still tetrahedral. But this time we have a lone pair of electrons. So I would have been more appropriate to draw this kind of like this. Now we still have the 3 hydrogens kind of making a little triangular base. So we're still trigonal. But notice that this will not be, actually it also kind of looks like a D4, but this will not be flat. So this is not trigonal planar, but rather trigonal pyramidal. So it kind of looks like a little pyramid, but only a 3-sided base instead of a 4-sided base. We're used to seeing 4-sided pyramids. This is a 3-sided base, but it still looks kind of like a pyramid. Trigonal pyramidal. I promise you, you would understand this. Everyone knows the shape of water. Everyone knows. Everyone knows that water is bent. Very few people understand why. But with oxygen as a central element, how many things around it? Right, set number 4. This time it has 2 atoms and 2 lone pairs of electrons. Because it has 4 things around it, its parent shape is still tetrahedral. But it has 2 lone pair. And those lone pair electrons are going to push the hydrogens closer together, roughly 108 degrees. Roughly 108 degrees. What's that shape? What's the shape of water? Water is a bent molecule. But why is it bent? Well, because those lone pair electrons, they want their space too. Let's just wrap this up real quick. Kim, we did right the left on the last one. You want to do the stick with the left or you want to go to the right?
Let's do the left.
Let's look at chlorine, Cl2. 4 things around it, still tetrahedral. But with 3 lone pairs, 4 minus 3 is equal to 1. Or if you prefer, they're just 2 atoms. 2 points always define a line. Linear. These tables can go as high as 5 and 6. We're going to stop at 4. You start getting some really beautiful structures. You go to higher numbers, but it's beyond the scope of this class, so we're not going to worry about it. Let's take a 5-minute break. I will see you at 10:50. And we are back. And yes, just talking with Kim, we're less than halfway through, but I figure about 4 more lessons and we're going to be approximately halfway through the course, which won't be next week, but the week after that. And next week, yes, we are going to start talking about actual factual chemical reactions, which is really what chemistry is all about. So we have started talking about molecular shape. We're going to start combining a couple of things now. What is electronegativity? Electronegativity, as you recall, is the attraction of an element for electrons. If you have a covalent compound, the electrons are being shared, but they don't have to be shared evenly, which gives rise to the concept of a polar bond, where you have one side that's slightly electronegative and the other side that's slightly electropositive. Let's talk about polar molecules. And this is an important concept because there's an old rule of thumb in chemistry. A phrase that actually has bad origins. I need to stop using that phrase. But there's an old concept in chemistry. It says like dissolves like. So what that means is polar compounds will dissolve in polar solvents. And we're going to talk about solutions actually in great detail a couple chapters from now. But it means that polar solutes will dissolve in polar solvents. Polar compounds will dissolve in polar solvents. Non-polar compounds will dissolve in non-polar solvents. So things like alcohol will dissolve in water. And when I say it dissolves, first of all, you can tell it dissolves because you end up with a clear, in this particular case, colorless. It doesn't always have to be colorless, but a true solution where the solute has dissolved in the solvent, it's always clear. Not necessarily colorless, but clear. If it does not dissolve, it may mix for a while, but you end up with a cloudy solution. So alcohol, you can mix it in any ratio you want, from 0 to 100% alcohol. My particular favorite alcohol is 0%. But you can mix it in any ratio that you want, and it dissolves. That's because both water and ethanol, we're going to talk about why, they're both polar molecules. On the flip side of the coin, maybe you like oil and vinegar dressing. Oil and vinegar do not mix. And you've seen this. You've seen oil sitting on top, a layer of oil sitting on top of a layer of water. And they just sit there. You can leave them forever, and they're never going to dissolve. So what do you have to do? You have to shake it up, which is something that men are very good at. And when you shake it up, you're going to mix the oil with the water, and you end up with a cloudy mixture, but not a true solution because it doesn't really dissolve. That's called the Tyndall effect, that cloudiness. It's called the Tyndall effect. And eventually, it'll separate back out again. Milk is not a true solution. The color of milk is not caused by calcium. Most people assume it's calcium. It is not. The color of milk is caused by a protein called casein. And casein does not dissolve in water. So you end up with this opaque mixture. It's not a true solution. It stands a very long time without separating, but anyone who has held on to milk long enough, you start seeing that yellowish white, that yellowish clear solution on top of the white. That's water. That's the casein separating out. In a mixture, it will eventually separate out. In a solution, in a true solution, it will not. So how do you know what's polar and what is not polar? Well, first of all, we have to understand if it is if you have no polar bonds, it's non-polar. Okay. In the first requirement to have a polar molecule is to have at least one polar bond. And how do you know if it's polar? You look at Pauling's electronegativity scale. You look at that table that we did a couple of days ago. You take the difference in electronegativity, and if the difference is greater than 0.5, but less than, forget where we set the upper end, 2.1, I think, or 1.8. I think it was 1.8. Anyway, if it's not ionic, you can ignore ionic because the concept of polar and non-polar doesn't really apply to ionic because we are not dealing with covalent bonds. So as long as it's not ionic and as long as the difference in electronegativity is greater than 0.5, you have a polar bond. Otherwise, it's nonpolar. I don't know the electronegativity of nitrogen. But it doesn't matter because nitrogen always has the same electronegativity. So the difference in electronegativity will be 0. This is nonpolar. If you have no polar bonds, it is not a polar molecule. Nitrogen will, well, I'm not going to use that as an example. Carbon has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. Like I say, the first period electronegativities are really easy to memorize because lithium starts with an electronegativity of 1, goes up by 0.5 every time. The difference in electronegativity is 1.0. So we definitely have polar bonds. The carbon is more polar than the oxygen is more polar than the carbon. So our polar bond is oriented this way. If you remember that sign, you point the arrow towards the more electronegative element. The little plus side goes towards the less electronegative element. That means that carbon is partial positive, oxygen is partial negative. So carbon dioxide must be a polar bond, right? No. And here's why. Carbon does not have a polar bond. It has two polar bonds. And they happen to be pointing in exactly opposite directions. In physics, we would be calling this vector analysis. But the concept is very simple. You have a wagon, you have a little red wagon, and it's being pulled by two kids. One of the kids is trying to pull it this way, the other kid is trying to pull it this way. As it turns out, these two kids are identical strength. Where's that little red wagon going to go?
No.
Nowhere. Those dipoles cancel each other out. Mathematically, they actually cancel each other out. So even though we have a polar bond, this is a highly symmetrical molecule. In a highly symmetrical molecule, if the polar bonds are identical strength, okay? Now, if you have oxygen on one side and let's say silicon on the other, okay, one of those kids is stronger than the other, is going to go the direction of the kid. So if you have identical elements bonded to the central element and a highly symmetrical shape, turns out the molecule will be nonpolar. Okay, does that kind of make sense? Okay. Let's look at water. Water, hydrogen is 2.1. Oxygen, as we said, is 3.5. So the difference in electronegativity there it is, 1.4. That's a pretty big difference in electronegativity. So yes, we have a polar bond. But how many polar bonds do we actually have? 2. All right. Again, same element bonded to the central element. So those two polar bonds are exactly the same strength. But notice that, how am I going to do this? Notice that instead of pulling, let's do it this way. Instead of the two kids pulling this way, now they're pulling this way. Where's that little red wagon going to go? It's going to go that way, isn't it?
Mm-hmm. Yep.
They may not be pulling in exactly the same direction, but they're not pulling in opposite directions. So it's going to go somewhere in between the two. Now we have a polar molecule with a net polarity that looks like this. So carbon dioxide is nonpolar. This is not highly symmetrical, so water is polar. Okay. Ethanol, as it turns out, is also polar. Carbon, actually, well, we can talk about that. Let's talk about it. Crying out loud, I brought it up. Let's talk about it. So ethanol And we did this as an example for Lewis dot structures. Each of these carbons is set number 4 with no lone pairs. So each of these carbons has a shape of tetrahedral. But the oxygen has 2 lone pairs. I'm going to reverse this. Actually, let me do this. So if we count the oxygen as a central element, there's actually a shorthand notation I could be using here. It's a bent molecule. And it has, as it turns out, the carbon-oxygen bond is polar. The oxygen-hydrogen bond is polar. So we have a polar molecule. We can actually treat the CH3CH2 group as the same. So I could have really, honestly, written this like this. We're going to treat this as one group. Doesn't matter that there are multiple atoms. It's only bonded to carbon. It's only bonded to one of the carbons. So this is what we're going to use for the shape, but you have that entire CH3CH2 here. And the polarity of the molecule looks like this. So what ends up happening, this is going to be a lie against concept across. It's going to interact with water this way. The partial negative side of the ethanol is going to be attracted to the partial positive side of the oxygen, of the water. And the partial positive side, Lord, I did these backwards. Excuse me while I erase my really silly mistake. This is the partial positive side. This is the partial negative side. This is the partial positive side. This is the partial negative side. My apologies for that error. Okay. But the same thing, the same concept applies. The partial positive side here is attracted to the partial negative side of the water. The partial negative side of the ethanol is attracted to the partial positive side of the water. Opposites attract. So the water is attracted to the ethanol, which is why the ethanol dissolves in water. There's an attraction there. Oil has no partial positive, partial negative sides. So there's nothing for the water to be attracted to. That's why it does not dissolve. We're going to, by the way, we're going to talk about intermolecular forces a few chapters from now. But this is the basic concept right here. Opposites attract. And that's kind of all there is. I kind of want to paint these walls dark now because as I do this, it's kind of hard to see my fingers. So I keep trying to get it so that it's at least the very dark closet behind me so you can see what I'm doing. But opposites attract, which is why polar solvents will dissolve in polar solutes and vice versa. Does that kind of make sense at all?
Yeah, it does.
Okay. So polar molecules, it's an important concept. So the question is, if you have the same element, like for example, if one of these was instead of oxygen, suppose this was sulfur on this side, this would be polar. Because if you have something other than oxygen, you have something, two different groups here, two different elements, it's not going to cancel out exactly. So something like COS, carbon in the center, oxygen on one side, sulfur on the other, that's going to be polar. Because the sulfur bond is not, that dipole is not going to cancel exactly with the other. I'm not quite sure what it would be, but it's not going to cancel exactly. But the question is, what is highly symmetrical? What shapes are highly symmetrical? Let's go back to our table. Here are our highly symmetrical shapes. Not all linear shapes are highly symmetrical. Actually, I'm going to do this over here. But set number 2, why don't I do that wrong? This one. Set number 2 with 0 lone pairs. Okay. Set number 2 with 0 lone pairs is highly symmetrical. Okay. Not all of them. Set number 2 with 1 lone pair is not symmetrical because you only have the central element bonding in one direction. Set number 3 with 0 lone pairs is highly symmetrical. You don't have them linear. They're not pointing in opposite directions this way, but the net dipole, you can do this, like I say, if you do vector analysis, these two dipoles will add up and cancel out this dipole. So set number 3 with 0 lone pairs is highly symmetrical. And set number 4 with 0 lone pairs. And notice it's all with 0 lone pairs. Tetrahedral is highly symmetrical as well. Okay. If we went on to the more extended version of VSEPR, you would see there are other molecular shapes that are also highly symmetrical, but for our purposes, we're going to stop here. Any questions?
Sir.
Okay. I would like to go back and revisit polyatomic ions since we do have a few minutes. As you recall, compounds with polyatomic ions, and I gave you a small list of polyatomic ions to figure out. You treat them just like they're simple ions. So if we look at something like calcium phosphate, we know the charge of calcium from the periodic chart. It is element number 20. And it's in the alkali earth metals. Therefore, the charge of calcium is always, always, always what?
2.
Plus 2. I asked you to memorize phosphate. Phosphate has the formula PO4. And its charge is always, always, always -3. You may not have those memorized yet. That's okay. So we do our cross check. In the formula for calcium phosphate, we will have 3 phosphates 3 calciums for every 2 phosphates. And that becomes the formula for calcium phosphate, right? Does that look right to you?
No.
Why? What does that kind of imply? Doesn't that kind of imply that we have 42 oxygens?
Yeah, that looks really wrong.
We don't have 42 oxygens, but we have 2 whats? We have 2 phosphate groups. In molecular formulas, sometimes you'll see parentheses like this. This is telling us that we have 2 of this entire group, phosphate. All right, 2 phosphates, which means we have 3 calciums. And this 2 applies to the phosphorus. So we have 2 phosphorus. And of course, we have 4 oxygens. We have 4 oxygens, am I right? You can call me dumb, Kim. It's okay.
No, it's not.
Because this 2 applies to everything inside the parentheses, but nothing outside the parentheses. So we have 3 calciums because this 2 does not apply to the calcium.
Right.
2 applies to both the phosphorus and the oxygen. My cat is destroying my house as we speak. So we don't have 4 oxygens. We have a total of 8 oxygens. 4 times 2 gives us 8 oxygens. And keep in mind, sulfate, as you recall, is SO4, also with a -2 charge. So we're going to do the same cross trick. Is that the correct structure? Is that the correct formula? What do you see there? Don't we have a common denominator?
Yeah, they cancel out, don't they?
Common denominators always cancel out in ionic compounds, not in covalent compounds, and now you understand why.
Oh,
Because
okay.
in covalent compounds, we have actually 4 carbons all bonded together. So we do not cancel out in covalent compounds, but in ionic compounds always cancel out that common denominator. This is still wrong. Why? If I only have 1 sulfate, do I need those parentheses?
No.
No. And when you look at CaSO4, you just recognize that group. You see, oh, sulfate, SO4. That's a sulfate. So you don't need the parentheses to point it out and just shove it in your face. This is sulfate. No, it's an SO4. It's a sulfate. We see it. So, any questions about the use of parentheses in ionic compounds? Okay. That takes us to 11:20. Thank you so much for participating. Don't be late for your next class. And I will see you next week.